kids, here we are, Stats with Glenn. I know that you've been looking forward to Chapter 8 all semester long, as have I. Chapter 8 is a natural extension of Chapter 7. It is essentially hypothesis testing if n is greater than 1. You might not have realized how weird it was in Chapter 7, but there was something really weird about the process. Do you remember in Chapter 7 when I chose one randomly selected student athlete, and I said that it was our friend Brooke, and we compared that score from that one randomly selected athlete with a comparison distribution representing an entire population. In real research, we're not usually going to get what we call an N of 1. If I really were going to try to test whether student athletes differ from the general population academically, I'm probably not really going to just randomly select one student athlete to compare against the general population. In fact, the more student athletes that I would choose would be the better. If I got 5 student athletes, that sample of 5 would be more representative of the entire population of student athletes. If I got 100 student athletes, that sample would be even more representative of the entire population of student athletes. And if I got 500 student athletes, then that sample would be even more representative of the population I'm trying to approximate and would instill more confidence in whatever findings I get. In Chapter 7, we went with an N of 1. The reason we went with an N of 1 is because, as I've said before, the logic and the math is sort of complicated enough as it is, and there is an additional mathematical process that we need to go through if n is greater than 1. And I didn't want to complicate things by throwing that additional process into Chapter 7. So Chapter 8 is just like Chapter 7, except now instead of that weird situation of an N of 1 representing the special population, we're now going to have a more realistic situation of an N greater than 1. Hypothesis testing if N is greater than 1. The main thing is that we're now going to be dealing with called a distribution of means. Okay, a distribution of means. I'll explain this in a bunch of different ways. But before, remember we had X. In that case, X was 93, if you recall in the last example. X was 93. With a distribution of individual scores, if I have an individual score representing my special population, one individual score, I will compare that individual score with a distribution of individual scores. However, what happens if instead of an individual score, let's say I get 5 scores. Let's say that I have 93, but I also have 92, 86, 51, and 99. Imagine this. Imagine if my sample representing my special population, and why not stick with the same example of whether student athletes perform differently, better or worse, than the general population of students academically. Imagine if I had not one individual score representing the special population, but imagine if I had 5 scores. Okay, so here's n equals 5. n equals 5, meaning I have 5 scores. Now, you've been sitting around in this class long enough that if you see 5 scores like that and you want to summarize those scores, you probably would do that using the mean. I'm not even going to bother computing the mean. I'm just going to tell you that that's what you would do. You would get the mean. And if we have a mean, I'm not going to compare a mean with a distribution of individual scores. A mean that represents a sample needs to be compared with a distribution of means. So it's a pretty simple idea. An individual score needs to be compared with a distribution of individual scores. A mean that represents a sample needs to be compared with a distribution of means. This is the core mathematical difference between Chapter 7 and Chapter 8. Now, what does a distribution of means look like? An important thing that you'll see is that the distribution of means varies as a function of n. So a distribution of means varies as a function of n. Before I get into the details of it, let me tell you that we now have slightly different or new parameters that we're going to be dealing with. Okay, because we might have a sample. We might have a distribution that represents a population, like we did in Chapter 7. Or we may now have parameters that represent a distribution of means. So we can have, like we had before, we can talk about the mean, we can talk about the variance, and we can talk about the standard deviation. With a sample, we've already gone through this. The mean is represented by m. Capital M, the variance is represented by SD squared, and standard deviation is represented by SD. With a population, the mean is represented by mu. Remember that Greek symbol mu thing we had talked about? The variance is represented by baby sigma squared, and the standard deviation is represented by baby sigma. If we're dealing with a distribution of means, which will be true for Chapter 8 and then into Chapter 9, the mean, you ready for this, kids? It is mu sub m. So that is the Greek mu and it's the English, I don't know if you call it English, whatever, regular m, capital M. Mu sub m. Mu sub m means the mean of a distribution of and we're going to throw that sub m at all these. So the variance of a distribution of means is sigma square sub m, meaning the variance of a distribution of means, and the standard deviation of a distribution of means is little baby sigma sub m, meaning the standard deviation of a distribution of means. For chapter 8, we're now going to be dealing primarily in this world, and we will largely be dealing with these particular parameters. What happens with a distribution of means is that as n increases, sigma sub m decreases. The really basic, simple thing, and I'll show you mathematically how this works, but the real basic thing that's happening is that as your n increases, your standard deviation of your distribution of means is going to decrease. Okay, so here's an example. Suppose this is n equals 1, and I'm going to give you mu equals 2.5, and I'm going to give you sigma equals 0.5. Okay, so I'm giving you GPA data. I'm saying that the population mean is 2.5, and this population standard deviation is 0.5. Okay, so similar kind of numbers that we've been working with prior examples. And let's say that n equals 1. If n equals 1, then we're dealing with a regular normal distribution. Sigma equals 2.5, or mu equals 2.5, sigma equals 0.5. Done. That's what we were doing in chapter 7. But here's something that happens. As n increases, so I'm going to give you n equals 5. As n equals 5, I'm going to give you a little bit of a formula here, and you'll see how it makes sense. Sigma square sub m equals sigma square divided by n. Okay, a little bit of a sidebar, but it's pretty important. The variance of a distribution of means equals the population variance it is based on divided by n. So as n increases, as your denominator increases, your variance of your distribution starts to go down. And it should not come as any surprise that sigma sub m simply is the square root of sigma square sub m. Okay, make a point of these equations right here. The reason that this rule up top is true is because of the math involved here. As n increases, your standard deviation of your distribution of means goes down. Okay, so now imagine a world where n equals 5. If n equals 5, our distribution of means that it's based on, it's a normal distribution, but it's a little bit The scientific term is squished. It's a little bit squished compared to this normal distribution over here. Now, the mean, mu sub m, is still 2.5. Okay, a very simple rule is that mu sub m equals mu. Okay, here's what it means if you're creating a distribution of means. A distribution of means based on an n of 5 is the equivalent of going into the distribution of individual scores that it corresponds to, randomly selecting 5 scores, getting the mean of those 5 scores, and putting those 5 scores back in. And then doing that infinitely. You think your job's boring. Then you go back in and you take 5 more randomly selected scores, you get the mean of those selected scores, and then you put them back. And you do that infinitely. That's what is happening. Now, how much those means vary from one another, they're going to vary from each other less compared with how much the individual scores vary from one another. So if you have an n of 5 and you're comparing means based on an n of 5, they're going to vary from each other less than the individual scores vary from each other. That's why this distribution gets squished. That's why sigma sub m, let's do the math on it. So to get sigma sub m, sigma square sub m equals sigma square divided by n, which is 0.5 times 0.5, which is 0.25 divided by n of 5, which is 0.05, and then sigma sub m is the square root of sigma square sub m, which is the square root of 0.05, which is 0.22. So here, okay, so kids, one way that I like to represent this idea is with a little friend I like to call the stat-friendly giant. Can we see him there, kids? Okay, look at what a nice friendly giant he is. So imagine, to think about a distribution of means based on a particular n, here's the idea. So imagine that he's going into this fishbowl. Imagine this is all 8,000 SUNY New Paltz students, the entire population. He's friendly, so he's not hurting anyone. He's going in there, he's grabbing 5 at a time, he's politely asking them their GPA, he's taking the average of those 5 students, and then he's gently, you see how gentle he is being, he's gently putting them back into the bowl, then he's grabbing 5 more, he's getting their GPA, and he's essentially collecting the data, but he's not collecting the data at the individual level. He's collecting the data in terms of the means based on the samples of 5. So that is the stat-friendly giant. My collaborator, Sarah Hall, who was a student of mine from a long time ago, co-wrote this with me. Her brother drew that picture, by the way. I'm just saying. So there's the stat-friendly giant for you. Thank you, Dana. So that is a visual designed to help you understand what it means to create a distribution of means. Now, take a look at sigma versus sigma sub m. What you see is that sigma sub m is smaller than sigma. And as n increases, sigma sub m will get smaller yet again. So let's throw an n of 10 at that. Okay, if we have an n of 10, here's the distribution. And you'll see I've made it even more squished. Even more squished, representing the idea that there is even less variability. Now, the stat-friendly giant is going into that fishbowl of 8,000 New Paltz students. He's grabbing 10 at a time, randomly selected, getting their scores, recording the mean, putting them back, and then getting another 10 randomly selected students, getting their mean, putting them back. And this graph represents those means based on an n of 10. So if you go in there and get an n of 10, how much are those means going to differ from each other? Not as much compared to the means based on an n of 5. To go really extreme, imagine if he went 1,000 deep. Imagine if he had a sample of 1,000, got the mean of that sample of 1,000, scored it, put everyone back, got another sample of 1,000, and he was comparing now means based on an n of 1,000. If we were doing that, those means would vary very little from each other. So sigma sub m would be really, really small in that case. As n increases, sigma sub m goes down, and this is why. So let's take a look at a distribution of means based on an n of 10. Okay, mu sub m, the mean of the distribution of means, always equals the mean of the population that it was drawn from. So that is going to equal 2.5. Okay, but sigma sub m is now going to be different. Okay, so here's the formula. First, we're going to do sigma square sub m, which is sigma square divided by n. Sigma is 0.5, so 0.5 squared, so 0.5 times 0.5 equals 0.25. Divided by n, remember n is now 10 in this example, so divided by 10 equals 0.025, or what I'm going to call 0.03. And then sigma sub m is the square root of sigma square sub m is the square root of 0.03, and that is 0.17. Okay, so let's take a look at it. If n equals 1, if it's a distribution of individual scores, the standard deviation is 0.5. If n equals 5, and the distribution is not individual scores, but it's a distribution of means based on random selections of 5 at a time, now our standard deviation, sigma sub m in this case, is 0.22. If n equals 10, our standard deviation of this comparison distribution, or this distribution of means, now is 0.17. As your n increases, your standard deviation of your distribution of means goes down. There's a real important implication for that regarding hypothesis testing, which is, as you'll see when we go through the process, as sigma sub m is smaller, your z obtained is going to be larger, the way that z obtained is calculated. We're going to go through the process in a little bit. And as z obtained is larger, it's more likely to be more extreme than z critical. You're more likely to reject the null hypothesis. So sometimes people will say, if you want to reject the null hypothesis, get a large n. This is the mathematical reason as to why that is specifically the case. As your n increases, your standard deviation of your distribution of means goes down. Okay, so let's go with an example. Let's go with that same example we went with before. Okay, do student athletes vary from the general population in their GPA? Okay, this is a two-tailed test. It's the same example that we used in the last example. Again, trying to sort of reduce the number of extra things you got to think about. I'm going to give you some information. Mu sub 2 equals 2.5. So the mean for the general population I'm putting again at 2.5. Sigma sub 2 I'm putting at 0.5. Standard deviation for the general population is 0.5. I'm going to give you an n now of 5. I'm going to give you the same alpha we had before of 0.05. And the one other piece of information I'm going to give you, I will tell you there's two ways I can give this to you. I can give you a bunch of scores. I could give you 5 scores, and you could compute the mean of those 5 scores, or I could just give you a mean of a sample of 5. And that's what I'm going to do in this case. It's a slight shortcut. I want you to understand what I'm doing here. So it's as if I'm a stat-friendly giant. I've gone into the pool of New Paltz student athletes, and I got their mean GPA, and I'm going to put that at, where am I going to put that? I'm going to put that at 3.5. Okay, so this is all the given information right here. Now remember, when it was just 3.4 with the individual case from chapter 8, we failed to reject the null hypothesis. Watch what happens now that we have an n of 5 and that the mean is slightly higher. Okay, so hypothesis testing. The 5 steps in hypothesis testing are always the same. Step number 1, articulate the research hypothesis and the null hypothesis. Okay, the research hypothesis. I'll put mu sub 1 is going to be student athletes. And I'm going to put mu sub 2 as students in general. Okay, so exactly the same as what we did in chapter 7. H sub 1. Remember, the way I worded this is a two-tailed test, right? Do student athletes vary from the general population in the GPA? I'm not specifying a particular direction. I'm not saying that do they score higher. I'm not saying do they score lower. I'm saying do they vary. So the research hypothesis is that mu sub 1 is not equal to mu sub 2. Okay, that's a classic two-tailed hypothesis. And the null hypothesis is that mu sub 1 equals mu sub 2. So this is actually identical to what we did in chapter 7 so far. Step number 1. Step number 2 is the main way that things are going to differ from chapter 7 to chapter 8. We're going to do a comparison distribution. But you remember, my comparison representing my special population is no longer an individual score randomly selected from that special population. It is now a mean based on 5 randomly selected scores. And since I'm going to compare a mean in my process, I need to compare that not with a distribution of individual scores, but rather with a distribution of means based on the appropriate n. So my comparison distribution is going to be a distribution of means. So the mean will be represented by mu sub m. I like to put the number 2 right there. I'm going to put that as optional. It's going to be more relevant for chapter 9 and more helpful for chapter 9, as we'll see. But 2 kind of as a vestige, because I use 2 to represent the general population. So here, I mean that this is a distribution of means that corresponds to the general population. That's what that little subscript of 2 is corresponding to. So that, remember, mu sub m equals mu. The mean of a distribution of means equals the mean of the population mean that it is drawn from. So mu sub m sub 2 equals 2.5. And sigma sub m sub 2 is the other piece of information that we need. So you remember, to get sigma sub m sub 2, sigma square sub m equals sigma squared divided by n. So this is the variance. Right now we're working on the variance for this comparison distribution. That's 0.5 squared over 5, which is 0.25 divided by 5, which is 0.05. And then sigma sub m sub 2 is the square root of sigma square sub m sub 2 is the square root of 0.05, which is 0.22, which you might recall, I believe we calculated that same number before. So this is our comparison distribution. It is a distribution of means. That's why it's a little bit squishier than a regular normal distribution. It has a mean of 2.5. Mu sub m sub 2 is the mean of the comparison distribution, which is a distribution of means. The standard deviation is represented by sigma sub m sub 2. I do like to say n equals 5 and kind of point to the distribution to remind us that this is a distribution of means based on a particular n, a particular sample size. Step number 3, ZCritical. If you played along with us for chapter 7, you'll see that this part's actually a repeat of what we've already done. ZCritical, so you remember alpha equals 0.05. The part of the distribution that we're defining as extremely low and unlikely to be due to chance is 0.05 or 5%. That is distributed across 2 different tails of our distribution. So we have 2 ZCriticals. This is 2.5% right here, half of 5%. This is 2.5% right here, half of 5%. This is 47.5% here. This is 47.5% here. If we go back to our table from page 325, we're going to look up 47.5%, which is actually on page 327, and it's right there. Percent mean to z, 47.5% corresponds to a z of 1.96. Meaning, so ZCritical equals plus or minus 1.96. A z of 1.96 or a ZCritical of negative 1.96 cuts off that section of the distribution that we were defining as extremely unlikely to be due to chance. extremely likely to come about from that distribution. So that's what those critical values are setting up. Step number 4, we're going to get Z obtained. Now, the Z-scores, to compute Z, there's a basic formula or a basic process which we've been doing all semester long, but now we're going to do it for a special case. In this particular case, Z obtained equals the particular sample mean of interest. Remember, this is a distribution of means. It's an infinite number of sample means based on an N of 5. So a score in a distribution of means is a mean. It is a sample mean. So the Z formula now is Z obtained actually equals M, meaning a sample mean, minus the mean of the comparison distribution mean, which is mu sub M sub 2, divided by the standard deviation of the comparison distribution, which is sigma sub M sub 2, which is 3.5 minus 2.5 divided by 0.22, which is 4.55. So Z obtained is 4.55. Let's take a look at what that kind of means. If I'm going to erase some of this over here. Okay, Z obtained is 4.55. Here's Z of 1.96. Here's Z of negative 1.96. Here's a Z of 0. Okay, I'll get out my little pink marker. A Z of 4.55 is almost off the charts, right? Z obtained equals 4.55. Remember, there's these two regions called the alpha region that we're defining as extremely unlikely to be due to chance. Our Z obtained is huge. 4.55 is like off the charts. How did that happen? A couple things. Our mean representing our special population of 3.5 was a lot higher than the mean for the general population of 2.5. So I was already stacking the deck. I was building in this idea that the student athlete's GPA was really high compared to the general population. And because I had an N of 5, my standard deviation for my comparison distribution started to go down. And because that went down, this was 0.22 compared to the general population standard deviation of 0.5, 0.22, suddenly I had a really big numerator, 3.5 minus 2.5, divided by a very small denominator of 0.22, that led to a really big Z obtained. Here's another way to think about it. I hate to do it, but I'm going to erase this whole thing here. Cover your eyes, kids. But here's another way to think about it. If my comparison distribution is over here, my comparison distribution, mu sub M sub 2 equals 2.5. Sigma sub M sub 2 equals 0.22. The fact that my Z obtained was way over there suggests something like this. It suggests that the population mean for student athletes is shifted relative to the mean for the general population. In other words, that Z of 4.55 was so outrageously high that it was really, really unlikely to come out of this distribution here, representing the general population, but it was much more likely to have come from a population over here where the mean is higher than is the mean for the general population. So when we are, step number 5, by the way, we're going to comment on the null hypothesis. So we'll comment on the null hypothesis. Because Z obtained was more extreme than Z critical, because Z obtained of 4.55 was much greater than a Z of 1.96, we reject the null hypothesis. We reject the null hypothesis. We reject the idea that the mean for the special population is equal to the mean for the general population. And we support this idea that the mean for the special population is different from, in this case, greater than the mean for the general population. So if your Z obtained is more extreme than your Z critical, you reject the null hypothesis and you're pretty much saying, I think the mean for my special population is not the same as the mean for the general population, because otherwise that would have been a totally wacky Z-score to have gotten a 4.55. Never would have happened. Very unlikely to have happened by chance alone. So that's statistically what it means when we are rejecting the null hypothesis. Dana, is there anything else on my agenda? All right, kids, chapter 8, distribution of means. This has been Stats or Glenn.